In the vast darkness of space, where silence reigns supreme and time moves differently than we can ever imagine, there travels a wanderer older than our entire solar system itself. This visitor has journeyed through the cosmic void for billions of years, crossing distances so immense that human minds struggle to comprehend their scale. It has witnessed the birth and death of countless stars, drifted through clouds of interstellar dust, and passed by worlds we will never see. Its name is 3I/Atlas, and it carries with it secrets from a time when our sun was not yet born and our planet Earth did not exist. This ancient traveler arrived in our neighborhood in the summer of 2025, moving faster than anything humanity has ever built, and it brought with it questions that challenge everything we thought we knew about the universe beyond our small corner of space. This is its complete story, from the moment it first appeared as a faint speck of light in a telescope to the revelations it continues to provide about the mysterious realm between the stars. Chapter 1: The Discovery Night. On the first day of July in the year 2025, in a remote observatory nestled in the Chilean mountains near a place called Rio Hurtado, an automated telescope system was performing its nightly routine of scanning the heavens for objects that might pose a threat to Earth. The telescope was part of a network called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, and its job was simple yet critically important: to watch the sky continuously and identify anything moving that might be dangerous. The night was clear and the stars shone brilliantly above the dry Chilean landscape, and the telescope's cameras were capturing thousands of images as they swept across different sections of the sky. Inside the telescope's computer systems, sophisticated algorithms were analyzing each image, comparing them to previous observations, and looking for anything that had moved or changed. At some point during that routine observation, the system detected something unusual. There was a faint object, barely visible even to the sensitive cameras, that appeared to be moving through space in a region near the constellations of Serpens Cauda and Sagittarius, not far from where the center of our entire galaxy lies in the sky. The object was given a temporary designation, a string of letters and numbers that meant nothing to anyone except the astronomers who would soon examine it more closely. The designation was a 11PL3Z, and it was moving at a speed that seemed strangely fast. The discovery observations were immediately transmitted to the Minor Planet Center, an organization run by the International Astronomical Union that keeps track of all the asteroids, comets, and other small objects in our solar system. When the data arrived at the Minor Planet Center, the scientists there began to analyze what had been found, and they quickly realized this was something worth paying attention to. The object's apparent brightness suggested it was relatively small, but its trajectory was peculiar. Initial calculations suggested it might be on a path that could bring it somewhat close to Earth's orbit, which is why it was temporarily listed on the Near-Earth Object Confirmation page, a special list maintained for objects that might need urgent follow-up observations. Within hours of the discovery announcement, telescopes around the world began turning their attention to this new visitor. Amateur astronomers with backyard telescopes joined professional scientists at major observatories in a coordinated effort to gather as much information as possible about the mysterious object. Every observation was crucial because each new data point would help determine exactly where this object came from and where it was going. Chapter 2: The Interstellar Revelation. As more telescopes observed the newly discovered object over the following hours and days, an extraordinary picture began to emerge from the accumulated data. The object was not following the kind of path that normal solar system objects follow. When astronomers calculated its orbit using the growing collection of observations, they found something that made them look twice at their calculations and check their work carefully. The object was moving on what scientists call a hyperbolic trajectory, which is a fancy way of saying it was moving far too fast to be captured by the sun's gravity. Every planet, asteroid, and comet that was born in our solar system follows an elliptical orbit, meaning they are gravitationally bound to the sun and travel around it in closed loops. But this object was different. Its speed and direction meant it was not going around the sun, but rather through our solar system, entering from one side and destined to exit from another, never to return. The implications of this trajectory were profound and exciting. This meant the object did not originate in our solar system at all. It had come from somewhere else, from the space between the stars that astronomers call interstellar space. It was only the third such visitor ever confirmed in human history. The first interstellar object, named Oumuamua, had been discovered in 2017 and had caused great excitement and debate in the scientific community. The second, named 2I/Borisov, had arrived in 2019. And now, in 2025, humanity had detected its third confirmed visitor from beyond our solar system. On July 2nd, just one day after the initial discovery, the Minor Planet Center made an official announcement that would capture the attention of astronomers and space enthusiasts around the world. They gave the object a new designation, 3I/Atlas. The number 3 indicated it was the third interstellar object. The letter I stood for interstellar, and Atlas was the name of the telescope system that had discovered it. The announcement confirmed that this mysterious visitor was indeed traveling through our cosmic neighborhood on a one-way trip, having come from the depths of space beyond our sun's influence. The excitement in the astronomical community was immediate and intense. Interstellar objects are incredibly rare and valuable opportunities for science because they offer a chance to study material that formed around other stars in other parts of the galaxy. They are like messages in bottles thrown into the cosmic ocean, carrying information about distant stellar systems and the processes that shape worlds far beyond our reach. Chapter 3: Uncovering its Ancient Past. When scientists began searching through archives of previous sky surveys, they made an interesting discovery. The object that would become known as 3I/Atlas had actually been photographed before its official discovery date, but nobody had noticed it at the time. These earlier images are called precovery observations, and they are incredibly valuable because they extend the time baseline over which the object's motion can be tracked, which allows for more accurate calculations of its orbit and origin. Researchers found images of 3I/Atlas in data from the Zwicky Transient Facility, another sky survey system, dating back to late May and throughout June of 2025. There were also earlier Atlas observations from June that had been captured but not immediately recognized as significant. One particularly early sighting came from May 21st at an observatory in Israel. The reason 3I/Atlas had not been discovered sooner, despite being photographed multiple times, was that it was passing in front of the galactic center, the densely packed heart of the Milky Way galaxy where billions of stars create a crowded and confusing background. Against this backdrop of countless stars, the faint, moving comet was extremely difficult to distinguish from the static background until it had moved far enough away from that crowded region. As astronomers analyzed the orbit and trajectory of 3I/Atlas using all available observations, they were able to trace its path backward through space and time. The calculations revealed something remarkable about where this ancient wanderer might have originated. Unlike the first 2 interstellar visitors, which had approached from the northern celestial hemisphere, 3I/Atlas came from the southern sky, from a direction roughly opposite to what astronomers call the solar apex. The solar apex is the direction our entire solar system is moving through space as it orbits around the center of the Milky Way galaxy. By studying the comet's velocity and trajectory, Scientists could estimate which region of our galaxy it likely called home before beginning its long journey through interstellar space. The evidence suggested that 3I/Atlas probably originated from somewhere within the Milky Way's disk, that flattened spiral structure where most of the galaxy's stars reside. More specifically, it might have come from either the thin disk, where younger stars live, or the thick disk, which contains older stellar populations. If 3I/Atlas came from the thick disk, that would make it extraordinarily ancient. The thick disk contains stars and other objects that formed when our galaxy was younger, and calculations suggested that if 3I/Atlas originated there, it could be anywhere from 7 billion to possibly even 11 billion years old. To put that in perspective, our entire solar system is only about 4.5 billion years old. This means 3I/Atlas could be more than twice as old as Earth, older than the Sun, older than any planet or moon in our neighborhood. It would have formed in the early days of the Milky Way galaxy when the universe itself was younger and different than it is today. Chapter 4: The Nature of the Visitor. In the early hours and days after the discovery, there was uncertainty about what exactly 3I/Atlas was. When astronomers find a new moving object in space, they need to determine whether it is an asteroid or a comet, and this distinction is more important than it might seem. Asteroids are typically rocky or metallic objects, the leftover building blocks from planetary formation, while comets are icy bodies that develop distinctive features when they approach the warmth of a star. Initially, some observers reported that 3I/Atlas appeared to be simply a point of light with no obvious signs of cometary activity. However, on July 2nd, multiple telescopes obtained clearer images of the object and noticed something significant. Observations from facilities including the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope on Mauna Kea all detected a faint, fuzzy appearance around the object. This fuzzy region is called a coma, and it is the hallmark signature of a comet. A coma forms when ice in a comet's nucleus begins to heat up and transform directly from solid to gas in a process called sublimation. As the ice turns to gas, it escapes from the comet's surface and creates a cloud that surrounds the solid nucleus at the center. The presence of a coma confirmed that 3I/Atlas was indeed a comet, not an asteroid. This meant it had an icy nucleus containing frozen materials from wherever it had formed billions of years ago. Some observations even suggested there might be a slight elongation to the coma, possibly indicating the beginning of a tail, though this feature was very faint and difficult to confirm at first. With the confirmation that it was a comet, 3I/Atlas received an additional designation following the naming conventions astronomers use. It was given the formal comet designation C/2025 N1 Atlas, where C indicates it is a non-periodic comet that will not return. 2025 is the year of discovery. N1 is a code indicating it was discovered in the first half of July, and Atlas is the Discovery Survey's name. As weeks passed and 3I/Atlas continued its journey toward its closest approach to the Sun, more and more telescopes observed it, and its cometary nature became increasingly obvious. The fuzzy coma grew larger and brighter as the comet approached the Sun, and its ices sublimated more vigorously in response to increasing solar heating. Professional astronomers using some of the world's most powerful telescopes confirmed that the coma had a reddish color, suggesting it contained dust particles along with gas. This coloration was similar to what had been seen in 2I/Borisov, the previous interstellar comet, and it told scientists something about the composition of material in the comet's nucleus. Chapter 5: Racing Toward the Sun. When 3I/Atlas was first discovered in early July 2025, it was located about 410 million miles from the Sun, which placed it within the orbital distance of Jupiter, the solar system's largest planet. At that time, it was traveling at approximately 137,000 miles per hour relative to the Sun, a speed that seems impossibly fast by human standards, but is not unusual for objects moving through the solar system. However, what made 3I/Atlas's velocity special was that it was too fast to be captured. Objects that are born in the solar system have velocities that match the gravitational influence of the Sun at their particular distance, but interstellar visitors arrive with additional velocity left over from their motion through the galaxy, called hyperbolic excess velocity. For 3I/Atlas, this excess velocity was calculated to be about 58 kilometers per second, or roughly 130,000 miles per hour. This is the speed the comet had when it was far from the Sun's influence, and it is the speed it will have again once it escapes back into interstellar space. As the comet fell inward toward the Sun, its speed increased due to the Sun's gravitational pull, just as a ball rolling downhill accelerates. By the time 3I/Atlas reached its closest point to the Sun, an event astronomers call perihelion, it was traveling at approximately 153,000 miles per hour. The date of perihelion was calculated to be October 29, 2025, and at that moment, the comet would be about 126 million miles from the Sun, placing it between the orbits of Earth and Mars. Fortunately for Earth, the geometry of the comet's path meant that our planet was on the opposite side of the Sun when 3I/Atlas made its closest approach, so there was never any danger of a collision. In fact, calculations showed that 3I/Atlas would never come closer than about 170 million miles to Earth, a comfortable and safe distance. During its approach toward perihelion, 3I/Atlas passed relatively close to Mars. On October 3, 2025, the comet sailed past the red planet at a distance of only about 18 million miles. While this might sound far, in astronomical terms it was quite close, and there was hope that some of the spacecraft orbiting Mars or operating on its surface might be able to observe the interstellar visitor. The trajectory also brought 3I/Atlas somewhat close to Venus earlier in its approach, though not nearly as close as its Mars encounter. As the comet approached the Sun, its activity increased dramatically. The coma surrounding its nucleus grew larger and brighter as more ice sublimated from the warming surface. By September and October, the comet had developed a visible tail of gas and dust streaming away from the Sun, pushed by solar radiation and the solar wind. This tail grew to impressive dimensions, stretching thousands or even tens of thousands of miles into space, though it remained faint and difficult to see without telescopes. Chapter 6: The Global Observation Campaign. As word spread through the astronomical community that an interstellar comet was passing through our solar system, researchers around the world mobilized to observe it with every available instrument. This kind of opportunity is extraordinarily rare, and scientists knew that every bit of data they could collect would be valuable for understanding not just this particular comet, but also the nature of interstellar space and the regions where such objects form. Ground-based telescopes across the planet took turns observing 3I/Atlas as Earth's rotation brought the comet into and out of view for different observatories. Facilities in both the northern and southern hemispheres contributed observations, capturing images in visible light, infrared light, and other wavelengths. Each wavelength revealed different aspects of the comet's composition and behavior. The Nordic Optical Telescope in the Canary Islands, operated by astronomers from Scandinavia, was among the first to confirm the comet's active nature and study its coma in detail. The Very Large Telescope in Chile, one of the world's most powerful ground-based observatories, used its sophisticated instruments to analyze the light coming from the comet's coma. Through spectroscopy, the technique of splitting light into its component wavelengths, astronomers could identify specific chemicals and elements present in the gas surrounding the comet. These observations revealed the presence of cyanide gas and nickel vapor, both of which are commonly seen in comets from our own solar system. Finding these familiar substances in an interstellar visitor was both reassuring and intriguing, suggesting that the basic chemistry of comet formation might be similar across different stellar systems. Polarimetric observations, which measure how light waves are oriented after reflecting off the comet, provided clues about the size and nature of dust particles in the coma. These studies revealed that 3I/Atlas's coma exhibited unusually high negative polarization, meaning much of the reflected light had its oscillations aligned in a particular direction. This characteristic is similar to what astronomers see when they observe trans-Neptunian objects, those distant icy worlds beyond Neptune's orbit in our own solar system, and it suggests that the comet's surface is composed of a mixture of icy material and very dark substances, possibly including carbon-rich compounds. As weeks turned into months, the observational campaign continued without pause. Researchers tracked the comet's brightness over time, measuring how it changed as the distance from the sun varied. They measured its rotation period by watching how the brightness flickered and varied with a regular rhythm, eventually determining that 3I/Atlas rotates once every 16.16 hours. They studied the color of the comet's coma and how that color changed over time as different ices sublimated and the surface composition evolved. These ground-based observations were incredibly valuable, but they were just the beginning of the scientific investigation. Chapter 7: Eyes in Space. While ground-based telescopes provided crucial observations, space-based observatories offered unique capabilities that could reveal aspects of 3I/Atlas impossible to see from Earth's surface. The atmosphere, while essential for life, is a hindrance for astronomy because it blocks many wavelengths of light and causes even visible light to shimmer and blur. Space telescopes overcome these limitations by orbiting above the atmosphere, providing crystal clear views and access to wavelengths that cannot penetrate to the ground. NASA's Transiting Exoplanet Survey Satellite, known as TESS, had actually observed 3I/Atlas before anyone knew what it was. TESS is designed to search for planets around other stars by watching for the tiny dimming that occurs when a planet passes in front of its star, but its wide-field cameras also capture many other objects. When astronomers checked TESS data after the comet's discovery, they found observations from May 7th through June 3rd, 2025. These early observations were particularly valuable because they showed that 3I/Atlas was already bright and active even when it was roughly 6.4 astronomical units from the Sun, far beyond the distance where water ice typically begins to sublimate. This strongly suggested that the comet's activity was being driven by more volatile substances, materials that vaporize at temperatures lower than water ice, such as carbon dioxide or carbon monoxide. On July 21, 2025, the Hubble Space Telescope, one of humanity's most famous and productive scientific instruments, turned its gaze toward 3I/Atlas. Hubble's cameras captured images that revealed the comet's coma in exquisite detail, showing its fuzzy structure and allowing scientists to measure its size more precisely. By carefully analyzing the brightness and distribution of light in Hubble's images, researchers were able to estimate that the solid nucleus at the center of all that gas and dust was probably smaller than 1 kilometer in diameter, and certainly no larger than about 5.6 kilometers. These observations helped constrain the comet's mass and composition. Later in the year, as 3I/Atlas passed through its perihelion and began its journey back toward interstellar space, Hubble observed it again. Images captured on November 30th showed the comet from a different perspective, with its coma still active and its tail still streaming away from the sun. These repeat observations allowed scientists to track how the comet's appearance changed over time as its activity waxed and waned in response to solar heating. Chapter 8: The James Webb Revelation. Perhaps the most significant space-based observations of 3I/Atlas came from the James Webb Space Telescope, the largest and most powerful space telescope ever built. Webb, which had only recently begun its scientific mission, has capabilities far beyond any previous space observatory, particularly in the infrared portion of the spectrum where heat radiation and molecular emissions shine brightly. On August 6, 2025, Webb pointed its sophisticated NIR-SPEC instrument at 3I/Atlas and captured data that would revolutionize scientists' understanding of the interstellar comet. NIR-SPEC is a spectrograph that operates in the near-infrared, and it can detect and measure the emission lines produced by specific molecules as they vibrate and rotate in the vacuum of space. The observations revealed the chemical composition of 3I/Atlas's coma with unprecedented detail. The results were announced by NASA on August 25th, and they were extraordinary. Webb's data showed that 3I/Atlas is unusually rich in carbon dioxide ice and gas. The amount of carbon dioxide relative to other substances was higher than what is typically seen in comets from our own solar system's Oort cloud or Kuiper belt. This discovery was significant because it suggested that 3I/Atlas might have formed in a different environment than our local comets, perhaps in a colder region of its parent stellar system or in a molecular cloud with a different chemical composition. In addition to the abundant carbon dioxide, Webb detected water ice, water vapor, carbon monoxide, and carbonyl sulfide. Each of these substances tells part of the story of the comet's formation and history. Water ice is the most common volatile substance in comets, while carbon monoxide is more volatile and only remains frozen at very low temperatures. The presence of carbonyl sulfide, a sulfur-bearing molecule, provided clues about chemical processes that occurred when the comet was young. The infrared images from Webb also showed how the brightness of the comet's coma varied depending on the wavelength of light observed. Certain wavelengths lit up brightly due to emission from carbon dioxide molecules, while others showed emission from water vapor. These variations created a kind of chemical map of the coma, revealing how different substances were distributed around the nucleus. The Webb observations were just the first of what will be multiple studies of 3I/Atlas. The telescope was scheduled to observe the comet again in December 2025, after perihelion, to see how its composition and activity might have changed as a result of its closest approach to the Sun. Chapter 9: The Composition Mystery. As data accumulated from the many observatories studying 3I/Atlas, scientists worked to piece together a comprehensive picture of what this ancient wanderer is made of and how it compares to comets native to our solar system. The chemical inventory revealed by spectroscopy was both familiar and strange. The presence of water ice was expected, as water is one of the most common molecules in the universe and is found in comets throughout our solar system. However, the relatively small amount of water compared to other substances was unusual. Most solar system comets are dominated by water ice with smaller amounts of other volatiles mixed in, but 3I/Atlas appeared to have a different balance. The abundant carbon dioxide was particularly intriguing. In our solar system, carbon dioxide ice is found in significant quantities on trans-Neptunian objects and in some comets, but it is usually not the dominant volatile component. The fact that 3I/Atlas contains so much carbon dioxide suggests it might have formed in an extremely cold environment where carbon dioxide could condense and remain stable while water was less abundant or had been lost through some process. Some scientists propose that 3I/Atlas might be similar to objects in our solar system's Kuiper belt or even to more distant bodies in the Oort cloud, but from a different stellar system. Others suggested it could represent a kind of object that is common in interstellar space but rare in our own solar system, perhaps a fragment from the disk of icy material that surrounded a young star billions of years ago. The detection of cyanide and nickel in the comet's coma added more pieces to the puzzle. Cyanide compounds, particularly hydrogen cyanide, are common in comets and are created by the breakdown of more complex organic molecules in the presence of sunlight. The fact that 3I/Atlas produces cyanide in similar amounts to solar system comets suggests that the basic chemical building blocks might be universal, formed by similar processes regardless of where in the galaxy a comet originates. Nickel vapor was more surprising. While metals have been detected in comets before, seeing nickel vapor at concentrations similar to those in solar system comets was noteworthy because it suggested that the incorporation of metal atoms into cometary ice might be a common process in planet-forming environments throughout the galaxy. Nickel and other metals in comets probably come from the tiny dust grains that were present in the protoplanetary disk where the comet formed, and those grains became embedded in the ice as it froze. Chapter 10: The Size and Structure Puzzle. One of the fundamental questions scientists wanted to answer about 3I/Atlas was how big it actually is. Knowing the size of a comet is important for understanding its mass, its potential to produce gas and dust as it approaches the sun, and for making comparisons with other comets and asteroids. However, measuring the size of a comet's nucleus is challenging because the nucleus is surrounded by the bright, fuzzy coma, and separating the faint nucleus from the surrounding glow requires careful analysis and powerful telescopes. The Hubble Space Telescope observations provided the best constraints on the nucleus size. By analyzing how much light came from the central region of the coma and making assumptions about how reflective the nucleus surface might be, astronomers calculated that the diameter of 3I/Atlas's nucleus is probably somewhere between about 440 meters and 5.6 kilometers. The most likely size, based on the available data, is less than 1 kilometer. For comparison, if the nucleus is around 1 kilometer in diameter, it would be similar in size to a modest mountain or a large city neighborhood. Despite its relatively small size, a 1-kilometer comet contains an enormous amount of material, potentially trillions of kilograms of ice and rock. The coma surrounding the nucleus was much larger than the nucleus itself, as is always the case with active comets. Observations by the SphereX mission in August 2025 revealed that the carbon dioxide coma had grown to about 700,000 kilometers in diameter, making it many times larger than the entire planet Earth. This enormous cloud of gas and dust was incredibly tenuous, with a density far lower than the best vacuum humans can create in laboratories, but its sheer size made it visible from vast distances. The question of how the nucleus is structured internally remained unanswered. Is it a single solid chunk of ice and rock, or is it a loose collection of smaller pieces held together weakly by their mutual gravity, what scientists call a rubble pile? Does it have distinct layers of different compositions, or is it relatively uniform throughout? These questions could not be answered with the available observations, but they are important for understanding how the comet formed and how it has evolved over its billions of years of existence. Chapter 11: The Dance with Planets. As 3I/Atlas continued its journey through the inner solar system in the fall of 2025, its trajectory brought it on close approaches to several of the Sun's planets, offering unique opportunities for observation and study. The comet had already passed relatively close to Venus during its inbound journey, though that encounter was not particularly close by astronomical standards. The flyby of Mars on October 3rd was more significant because several operational spacecraft were orbiting Mars at that time, and there was hope that they might catch a glimpse of the interstellar visitor. The distance of approximately 18 million miles was still too far for detailed observations from Mars' orbit, but the event captured the imagination of mission planners and the public. As 3I/Atlas swung past its perihelion point on October 29th, it entered a brief period when it passed behind the Sun from Earth's perspective, an event called solar conjunction. During solar conjunction, which occurred on October 21st, observations from Earth-based telescopes became difficult or impossible because the Sun's glare overwhelmed the faint comet. This observational gap lasted until early November, when 3I/Atlas emerged on the other side of the Sun and became visible again to ground-based observers. On November 1st, astronomical observations resumed, and researchers eagerly examined the comet to see how it might have changed during its perihelion passage. The months following perihelion would see 3I/Atlas gradually moving away from the Sun, its activity slowly declining as the reduced solar heating caused less ice to sublimate. However, the comet would remain observable for many more months as it journeyed outward. One of the most anticipated future encounters would occur in March 2026, when 3I/Atlas is predicted to pass relatively close to Jupiter, the solar system's giant planet. While close is a relative term and the comet will not be in danger of colliding with Jupiter, this encounter could potentially cause slight changes to the comet's trajectory through the subtle gravitational influence of Jupiter's immense mass. Astronomers plan to observe this encounter carefully to see if any measurable changes occurred, and to study the comet as it passed through different regions of the solar system's environment. Chapter 12: The Rotation and Activity Pattern. By carefully monitoring the brightness of 3I/Atlas over many nights, astronomers discovered that it rotates, tumbling end over end as it travels through space. The rotation period was measured to be approximately 16.16 hours, meaning the comet completes one full turn roughly 2/3 of the length of an Earth day. This rotation creates subtle variations in the comet's brightness because different parts of the nucleus surface have different reflectivities and because the viewing angle changes as the comet spins. The discovery of the rotation period provided clues about the comet's physical properties. The rate at which an object rotates is related to its formation history and the physical processes it has experienced. A rapidly spinning comet might have been set spinning by an ancient collision or by the rocket-like effect of gas jets erupting from its surface, while a slowly rotating comet might indicate a more gentle history. The 16-hour rotation period of 3I/Atlas is not particularly fast or slow compared to other known comets, suggesting a typical formation and evolution. As 3I/Atlas approached the Sun, its activity increased in a predictable pattern. When it was far from the Sun, beyond about 4 or 5 astronomical units, only the most volatile substances like carbon monoxide and carbon dioxide were sublimating, creating a faint coma. As the comet moved closer and the surface temperature increased, water ice began to sublimate in addition to the more volatile ices, and the coma grew brighter and larger. The rate at which gas was being produced increased dramatically during the weeks leading up to perihelion. Observations by the James Clerk Maxwell Telescope in September measured the production rate of hydrogen cyanide gas and found it was increasing over time as the comet approached the Sun. On September 7th, the production rate was measured at about 1.5 times 10 to the 25th molecules per second, and just 1 week later it had climbed to 4.5 times 10 to the 25th molecules per second, representing a tripling in just 7 days. This acceleration of activity was exactly what scientists expected based on how solar heating affects cometary ices. The brightness of 3I/Atlas as seen from Earth also changed over time, becoming brighter as it approached and then gradually fading as it moved away after perihelion. At its brightest, the comet reached an apparent magnitude of approximately 11.5, which made it visible through small telescopes and even through large binoculars under dark skies, though it remained invisible to the unaided eye. Chapter 13: The Military Implications. Although 3I/Atlas posed no actual threat to Earth, its appearance in our solar system and its unusual characteristics prompted discussions within military and defense organizations about how to detect and track objects entering the solar system from interstellar space. The comet's high velocity and its trajectory coming from an unexpected direction raised questions about whether current detection systems would be adequate if a dangerous object were ever to approach from interstellar space. Several news reports and articles discussed how 3I/Atlas had, in an indirect way, become a test case for planetary defense capabilities. The global network of telescopes that monitor near-Earth space is primarily designed to detect asteroids and comets that are already in solar system orbits, following predictable paths that can be calculated years or decades in advance. Interstellar objects are different because they appear suddenly, moving on trajectories that do not match the familiar patterns of solar system orbits. The fact that 3I/Atlas was discovered several months before its closest approach to Earth, and that its trajectory was quickly determined to pose no danger, was viewed as a success for the astronomical detection networks. However, if an interstellar object were ever found to be on a collision course with Earth, the lead time available for any potential response would be much shorter than for a typical near-Earth asteroid. Military tracking stations in various countries that monitor space for satellites and potential threats also turned their attention to 3I/Atlas. Reports suggested that at least 2 military facilities recorded observations of the comet and shared data with civilian astronomers. These observations helped refine the comet's trajectory and provided additional data points for orbit calculations. The cooperation between military and civilian observers highlighted how the tracking of unusual space objects benefits from contributions across different sectors of society. For military space surveillance systems, 3I/Atlas provided a valuable real-world scenario for testing detection algorithms and tracking procedures that had largely been theoretical until now. The comet's rapid motion and unusual trajectory forced systems to adapt and improve, lessons that could prove valuable if future interstellar visitors are detected. NASA even added 3I/Atlas to a monitoring list maintained by the Interstellar Object Studies Group, marking the first time in history that such a designation had been given to an active comet from beyond the solar system. Chapter 14: Comparing the Visitors. With 3 confirmed interstellar objects now in the record books, scientists had the opportunity to compare them and look for patterns that might reveal something about the population of objects drifting through interstellar space. The first visitor, 1I/Oumuamua, discovered in October 2017, remains the most mysterious and controversial. Oumuamua showed no signs of cometary activity, no coma or tail, and its highly elongated shape, inferred from brightness variations, was unlike anything commonly seen in solar system asteroids or comets. Its trajectory showed slight, unexplained accelerations that were difficult to account for using conventional cometary outgassing models, leading to much speculation and debate, including controversial suggestions that it might be an artificial object from an extraterrestrial civilization, though most scientists consider natural explanations far more likely. The second interstellar visitor, 2I/Borisov, discovered in August 2019, was more straightforward. It was clearly a comet with a bright coma and tail, and its composition and behavior were remarkably similar to comets from our solar systems or cloud. Spectroscopic observations showed familiar substances like water, carbon monoxide, and various organic compounds. Borisov provided reassuring evidence that comets from other stellar systems can be quite similar to our own, suggesting universal processes of comet formation. Now 3I/Atlas added a third data point. Like Borisov, it was unambiguously a comet, with clear cometary activity and a composition that included many familiar substances. However, 3I/Atlas also showed distinctive characteristics that set it apart. Its unusually high carbon dioxide content made it compositionally different from typical Oort cloud comets in our solar system, suggesting diversity in the interstellar comet population. Its apparent age, potentially billions of years older than our solar system, made it possibly the most ancient object ever studied up close by human science. By comparing the three interstellar objects, astronomers could begin to estimate how common such visitors might be. Statistical calculations suggested that at any given time, there might be one or more interstellar objects passing through the inner solar system, but most go undetected because they are small, faint, or simply not looked at by telescopes pointed in the right direction at the right time. As detection systems improve and more powerful telescopes come online, such as the Vera C, Rubin Observatory, which had actually photographed 3I/Atlas during test observations before its official discovery, the detection rate for interstellar objects is expected to increase dramatically. Within a few years, it might become routine to discover several such visitors each year. Chapter 15: The Origin Question. One of the most profound questions about 3I/Atlas was where exactly it came from. Tracing the trajectory of an interstellar object backward through space and time is an immense challenge because small uncertainties in the measured velocity and position grow larger the farther back in time one tries to calculate, and because the gravitational influences of all the stars the object passed during its journey must be considered. Astronomers used sophisticated computer simulations to trace 3I/Atlas's path backward for millions of years. The calculations suggested that the comet had been traveling through interstellar space for an immense period, perhaps hundreds of millions or even billions of years, before encountering our solar system. During that time, it may not have had a close encounter with any star, drifting in the vast darkness between stellar systems where temperatures hover just a few degrees above absolute zero. The direction from which 3I/Atlas approached suggested it came from somewhere within the Milky Way's disk rather than from the halo of old stars that surrounds the galaxy. More specifically, scientists proposed that its origin might lie in the boundary region between the thin disk and the thick disk of the galaxy. The thin disk is where most of the Milky Way's stars currently reside, including our Sun, while the thick disk is a population of older stars and associated objects that formed when the galaxy was younger. If 3I/Atlas indeed originated from the thick disk, it would be a relic from an earlier epoch of the galaxy's history, a time when star formation was more vigorous and the chemical composition of interstellar gas and dust was different from today. The age estimates for 3I/Atlas ranged from about 3 billion years to possibly as much as 14 billion years, with values around 7 to 11 billion years considered most likely. A 7-billion-year-old comet would have formed about 2.5 billion years before our solar system began to coalesce from its own cloud of gas and dust. An 11-billion-year-old comet would have formed in the very early history of the galaxy, less than 3 billion years after the Big Bang itself. The idea that humans were observing and studying an object that might predate the Sun and Earth by billions of years was humbling and awe-inspiring. This ancient wanderer had witnessed the galaxy's evolution, seen countless generations of stars born and die, and finally, by chance, wandered into a solar system where an intelligent species had developed the technology to detect and study it. Chapter 16: The Public Fascination. As news of 3I/Atlas spread beyond the astronomical community to the general public through media coverage and social media posts, the interstellar comet captured the imagination of people around the world. There is something inherently captivating about the idea of a visitor from beyond our solar system, a tangible connection to the vast universe beyond our familiar neighborhood of planets and moons. Science communicators and educators used 3I/Atlas as a teaching opportunity, explaining concepts like orbital mechanics, spectroscopy, and the formation of comets to audiences who might not normally follow astronomical news. The comet became a trending topic on various social media platforms, with amateur astronomers sharing their own images captured through backyard telescopes. As with previous interstellar objects, especially Oumuamua, there was speculation and discussion about the possibility that 3I/Atlas might not be entirely natural. Some suggested it could be an alien spacecraft or probe, perhaps sent by an advanced civilization to explore our solar system. While such ideas make for exciting science fiction, scientists emphasized that all the evidence pointed to 3I/Atlas being a natural comet, with behavior and composition entirely consistent with an icy body formed by natural processes. NASA held a press conference in November 2025 to present the latest findings about 3I/Atlas and to address questions from the media and the public. During this event, scientists displayed stunning images from Hubble and other telescopes, explained the chemical composition revealed by spectroscopy, and discussed what the comet could teach us about conditions in other parts of the galaxy. The officials emphasized that while 3I/Atlas is fascinating scientifically, it poses no danger to Earth and that its study is purely about advancing human knowledge of the cosmos. Educational institutions incorporated 3I/Atlas into their curricula as a current events topic in science classes. Students around the world learned about interstellar space, the life cycles of stars and planetary systems, and the methods scientists use to study distant objects. The comet became an example of how scientific discovery happens in real time and how researchers from many countries collaborate to understand new phenomena. For many people, 3I/Atlas sparked a sense of wonder about the universe and a desire to learn more about astronomy and space science. It served as a reminder that the cosmos is full of surprises and that human knowledge, while impressive, still has much to discover. Chapter 17: The Technical Challenges of Observation. Observing 3I/Atlas presented numerous technical challenges that tested the capabilities of both ground-based and space-based telescopes. The comet was never particularly bright, remaining at or below the limit of visibility for the human eye even at its peak. This meant that detecting and studying it required sensitive cameras and large telescopes that could gather enough light to form clear images. From ground-based observatories, the challenge was compounded by Earth's atmosphere. Turbulence in the air causes stars and other celestial objects to twinkle and shimmer, an effect that astronomers call seeing. On nights when the seeing is poor, images become blurred and details are lost. Observatories had to wait for nights with good atmospheric conditions to obtain the sharpest images of the comet. Additionally, the position of 3I/Atlas in the sky changed over time as it moved along its trajectory and as Earth orbited the Sun, meaning that observatories at different latitudes had varying windows of opportunity to observe it. The faintness of the comet also meant that long exposure times were necessary to capture enough light. During these long exposures, which could last several minutes, the telescope had to track the comet's motion across the sky with high precision, otherwise the comet would appear as a streak rather than a point of light. This tracking requirement was particularly challenging because 3I/Atlas was moving relatively quickly compared to background stars. For spectroscopic observations, where the light from the comet is spread out into a rainbow spectrum to identify chemical signatures, even more light was needed. Obtaining good spectra required large telescopes and sophisticated instruments, and even then, Some chemical species were present in such small quantities that detecting them required carefully combining data from multiple nights of observation. Space-based telescopes like Hubble and Webb avoided the problems of atmospheric distortion but had their own constraints. These telescopes are shared resources with busy schedules, and observations must be planned weeks or months in advance. The brightness and position of 3I/Atlas had to be predicted accurately so that the telescopes could be pointed at the right location at the right time. Once observations were obtained, the data had to be carefully calibrated and processed to remove instrumental effects and extract the scientific information. Coordinating observations across multiple telescopes and facilities required international cooperation and careful planning. Astronomers from different countries and institutions had to share data, coordinate observing schedules to avoid duplication of effort, and work together to interpret the results. This collaboration was facilitated by modern communication technology and by the shared values of the international scientific community. Chapter 18: The Alien Question Revisited. Despite overwhelming evidence that 3I/Atlas is a natural comet, questions and speculations about the possibility of it being artificial or associated with extraterrestrial intelligence periodically surfaced in public discussions and some fringe scientific circles. This pattern of speculation has become familiar whenever an unusual object from interstellar space is detected, and it reflects both the human fascination with the possibility of extraterrestrial life and a tendency to find patterns or intentions in natural phenomena. Avi Loeb, a prominent astronomer at Harvard University who has been vocal about considering unconventional hypotheses for interstellar objects, wrote articles discussing 3I/Atlas and whether its properties might indicate artificial origins. Loeb has argued that the scientific community should not dismiss the possibility of artificial objects too quickly and should consider all hypotheses, even unlikely ones, as long as they can be tested. However, the mainstream scientific consensus was clear that 3I/Atlas exhibits all the hallmarks of a natural comet. Its composition, with abundant ices like carbon dioxide and water that sublimate in response to solar heating, is exactly what would be expected from an icy body formed in a protoplanetary disk billions of years ago. The development of a coma and tail, the detection of dust particles and gas molecules in the coma, the variations in brightness consistent with rotation and variable activity, all of these observations fit naturally into the framework of cometary science developed through decades of studying solar system comets. No credible evidence suggested artificial structures, anomalous acceleration inconsistent with outgassing, or signals that might indicate technology. NASA officials specifically addressed these speculations during their public announcements about 3I/Atlas, stating clearly that the object is of natural origin and that scientists have found no signs of alien technology. The discussion about possible artificial origins, while largely dismissed by working astronomers, did serve to engage public interest and to highlight the fact that interstellar objects are scientifically valuable regardless of whether they are natural or artificial. Each detected interstellar visitor provides data about the environment between stars and the populations of objects that drift through the galaxy. As detection rates increase in coming years and dozens or hundreds of interstellar objects are found, patterns will emerge that will help scientists understand how these objects form, how common they are, and what diversity exists in the interstellar population. Chapter 19: The Ongoing Journey. After passing perihelion on October 29, 2025, 3I/Atlas began the outbound leg of its journey through our solar system, gradually moving away from the sun and heading back toward the interstellar space from which it came. As the distance from the sun increased, the solar heating that had driven the comet's activity began to diminish, and the rate of gas and dust production started to decline. The coma slowly faded and shrank as less material escaped from the nucleus. However, the comet remained under observation. Astronomers continued to track its position, measure its brightness, and study its changing appearance as it moved into the outer solar system. In the months following perihelion, 3I/Atlas would pass through the orbital distances of Mars, then Earth, and later the asteroid belt. The predicted close approach to Jupiter in March 2026 was eagerly anticipated, as it would provide another opportunity to observe the comet and to see if Jupiter's gravity caused any measurable changes to its trajectory. As 3I/Atlas moves farther from the Sun, it will eventually become too faint for all but the largest telescopes to observe. Sometime in late 2026 or 2027, the last images will be captured, and the comet will fade from view, returning to the darkness of interstellar space where it will continue its eternal wandering through the galaxy. The time it spent in the inner solar system, where it was bright enough to study, will have been just a few months out of the billions of years of its existence, a brief illuminated moment in an otherwise dark journey. Where will 3I/Atlas go next? Its trajectory has been measured with enough precision that astronomers can calculate its future path for millions of years. It will exit our solar system traveling in a specific direction, though the exact details of its future encounters with other stars are impossible to predict with certainty because of the cumulative effects of many small gravitational influences over such vast timescales. It might pass relatively close to another star in a few million years, or it might drift through empty space for tens or hundreds of millions of years before experiencing another stellar encounter. Perhaps one day, in the unimaginably distant future, 3I/Atlas will pass through another planetary system, and if intelligent beings are there with telescopes, they might see it just as we have and wonder about its ancient history and its journey through the galaxy. Chapter 20: The Scientific Legacy. The study of 3I/Atlas will leave a lasting legacy in multiple fields of astronomy and planetary science. Every paper published about the comet, every spectrum obtained, every image captured adds to the growing library of knowledge about interstellar objects and the diversity of small bodies in the galaxy. One major contribution is simply the detection itself. With 3 confirmed interstellar objects now in the record books, scientists can begin to make statistical estimates about how common such objects are. The fact that 3 have been detected in less than a decade suggests that many more exist and that improving detection capabilities will lead to more discoveries. This information helps constrain models of planetary system formation and evolution because it tells us how many small bodies are ejected into interstellar space during the chaotic early periods when planets are forming and gravitationally interacting. The detailed compositional measurements of 3I/Atlas provide a benchmark for understanding the chemistry of planet formation in other stellar systems. The high carbon dioxide content compared to water suggests that the region where 3I/Atlas formed might have been colder or chemically different from the region where solar system comets formed. By studying many interstellar comets over time, astronomers will be able to map out the diversity of chemical conditions in different parts of the galaxy and in different epochs of galactic history. The observations of 3I/Atlas also advance technical capabilities. The rapid response of the global astronomical community, the coordination of observations across many facilities, and the sophisticated analyses performed on the data all represent improvements in how such events are handled. When the next interstellar visitor is detected, scientists will be even better prepared to extract maximum scientific value from the limited time the object is observable. NASA's observations with Hubble, Webb, and other flagship missions demonstrated the value of maintaining powerful space-based observatories with flexible scheduling that can respond to unexpected targets of opportunity. These missions were designed primarily for other purposes, such as studying distant galaxies or searching for planets around other stars, but their ability to turn quickly to observe a passing interstellar comet showcased their versatility. Future missions and observatories will be designed with similar flexibility in mind, ensuring that when rare and valuable targets appear, the tools are available to study them. The study of 3I/Atlas also highlighted the importance of archival data. The Recovery observations from May and June, found by searching through data that had already been collected for other purposes, proved invaluable for refining the comet's orbit and extending the baseline of observations. This underscores the value of maintaining comprehensive archives of sky surveys and making that data accessible to researchers. Many future discoveries may come from mining archives for objects that were present in images but not noticed at the time. Chapter 21: The Questions That Remain. Despite the wealth of observations and the detailed analyses performed by researchers around the world, many fundamental questions about 3I/Atlas remain unanswered, and some may never be fully resolved. The exact size of the nucleus is still uncertain within a range of possibilities. Is it closer to 400 meters or closer to 5 kilometers in diameter? The answer matters for understanding the comet's mass, its structural strength, and how much material it could potentially lose through outgassing over its lifetime. To answer this definitively would require either a much closer approach to the Sun, where the nucleus might heat up enough for its surface to become visible separately from the coma, or a visit by a spacecraft, which is not feasible for an object moving so fast and already departing the solar system. The internal structure of the nucleus is completely unknown. Is it a solid chunk of primordial ice and rock that has remained largely unchanged since its formation billions of years ago? Or has it been processed by heat and impacts over the eons? Does it have layers of different compositions like an onion, or is it a homogeneous mixture? These questions could only be answered by a dedicated mission that could study the comet up close, perhaps even landing on its surface or extracting samples for analysis. The exact age of 3I/Atlas remains uncertain. While scientists can estimate that it is very old, possibly 7 to 11 billion years, pinning down the precise age is impossible without knowing exactly where and when it formed. Different formation environments and different stellar systems would have produced comets of similar composition but different ages. Unless we could somehow trace the comet's trajectory back to a specific star system and know that system's age, the age of 3I/Atlas will remain an educated guess based on statistical arguments. The question of whether 3I/Atlas has siblings is also intriguing. When planetary systems form, many small bodies are typically ejected into interstellar space. This means that somewhere in the galaxy, there might be many objects that formed in the same stellar system as 3I/Atlas, ejected at different times and now scattered across light years of space. The chances of detecting one of these siblings is vanishingly small, but the thought that they exist adds to the sense of mystery. What events led to 3I/Atlas being ejected from its home system? Was it a close gravitational encounter with a gas giant planet, similar to how Jupiter sometimes flings comets out of our solar system? Was its parent star in a binary system, and did the companion star's gravity disturb the comet's orbit? Or did something more dramatic happen, such as a close pass by another star that disrupted the entire planetary system? These questions cannot be answered with available data, but illustrate how much remains unknown about the comet's history. The possibility that 3I/Atlas has experienced changes during its long journey is worth considering. Has it been modified by exposure to cosmic rays, by slow chemical reactions occurring at cryogenic temperatures, or by rare collisions with interstellar dust grains? The surface we observe today might not be the same as the surface that existed when the comet was young. Understanding these slow evolutionary processes is important for interpreting what we see. Chapter 22: Comparative Planetology Beyond the Solar System. The study of interstellar objects like 3I/Atlas opens a new chapter in comparative planetology, the science of understanding planets and small bodies by comparing examples from different systems. For decades, planetary scientists could only study objects in our own solar system, drawing conclusions about planetary processes from the 8 planets, dozens of moons, and millions of asteroids and comets that share the Sun's gravitational domain. The discovery of exoplanets, planets orbiting other stars, expanded this comparative framework, though exoplanets can only be studied remotely and in limited detail given current technology. Interstellar objects provide a middle ground. They are samples from other stellar systems, but unlike distant exoplanets, they come close enough to Earth that we can study them in detail with telescopes and instruments. They are like free samples delivered to our doorstep, allowing direct analysis of material that formed elsewhere in the galaxy. By comparing 3I/Atlas to solar system comets, researchers can identify similarities and differences that reveal universal processes versus local peculiarities. The presence of cyanide and nickel in 3I/Atlas, for example, suggests that the basic chemistry of comets may be similar across the galaxy, formed by similar reactions in protoplanetary disks around young stars. On the other hand, the unusual carbon dioxide richness suggests that temperature or chemical conditions can vary significantly, producing comets with different ice compositions. As more interstellar objects are discovered and studied, patterns will emerge. Are carbon dioxide-rich comets common or rare? Do comets from different parts of the galaxy show systematic differences in composition that might reflect the chemical evolution of the galaxy over time? Are there types of objects in interstellar space that are not represented in our solar system, perhaps because the conditions that produce them did not exist in the early solar nebula? These questions can only be answered through a statistical sample of many interstellar visitors. The diversity within our own solar system's small body populations is enormous, ranging from rocky asteroids to icy comets to objects like Pluto that blur the boundaries between categories. Interstellar space likely contains even greater diversity, samples from billions of stellar systems with different formation histories and environments. Each new interstellar visitor will add to our understanding of this diversity and help us place our own solar system in context. Are we typical or unusual? Do our planets and small bodies represent common outcomes of star and planet formation, or are we an outlier in some ways? These profound questions about our place in the galaxy can only be addressed by studying the cosmos beyond our own stellar neighborhood. Chapter 23: The Technology of Discovery. The discovery and study of 3I/Atlas showcased the sophisticated technology and techniques that modern astronomy employs to detect and characterize faint, fast-moving objects in the vastness of space. The Atlas telescope system that made the discovery is an automated sky survey designed to scan large areas of the sky repeatedly, looking for anything that changes or moves. The system consists of multiple telescopes at different locations, all equipped with wide-field cameras that can image large swaths of sky in a single exposure. Computer algorithms analyze the images in near real time, comparing new observations to catalogs of known objects and flagging anything unusual for human review. This automated approach is necessary because the volume of data is too large for humans to examine manually. A single night of observations can produce hundreds of thousands of images, and within those images might be a handful of genuinely interesting objects mixed in with millions of known stars, galaxies, and solar system bodies. Only sophisticated software can efficiently separate the signal from the noise. When Atlas detected 3I/Atlas, the system didn't immediately know it was interstellar. It simply flagged a moving object that appeared in multiple images and submitted the observations to the Minor Planet Center. Only after additional observations were collected and orbits calculated did the interstellar nature become apparent. This illustrates the importance of follow-up observations and international collaboration. No single observatory could have characterized 3I/Atlas alone. It required contributions from many facilities. The spectroscopic techniques used to determine the comet's composition are marvels of modern physics and engineering. A spectrograph splits light into its component wavelengths with high precision, and by measuring the brightness at each wavelength, astronomers can identify specific atoms and molecules by their unique spectral fingerprints. For 3I/Atlas, spectrographs on telescopes like the Very Large Telescope and the James Webb Space Telescope revealed carbon dioxide, water, cyanide, nickel, and other substances by detecting the specific patterns of bright and dark lines these substances produce in the spectrum. Infrared observations by Webb required cooling the telescope and instruments to incredibly low temperatures to eliminate heat radiation from the telescope itself that would otherwise swamp the faint signal from the comet. Webb operates at temperatures only a few tens of degrees above absolute zero, maintained by massive sun shields and advanced cryogenic systems. This extreme engineering makes it possible to detect the faint infrared glow from molecular vibrations and thermal emission in the comet's coma. Hubble's observations required precise pointing and tracking despite the telescope being in orbit, moving around Earth at thousands of miles per hour. Onboard gyroscopes and guide stars allow Hubble to point with exquisite accuracy and track moving targets smoothly during exposures. The images of 3I/Atlas captured by Hubble reveal details smaller than the width of a human hair seen from across a football field, a testament to the telescope's remarkable optical quality and stability. Chapter 24: The Educational Impact. The passage of 3I/Atlas through our solar system provided educators and science communicators with a valuable opportunity to engage students and the public with real-world, current science. Unlike historical events or theoretical concepts that can seem distant or abstract, the comet was happening in real time, with new observations and discoveries being announced regularly. Teachers incorporated the story of 3I/Atlas into lesson plans across multiple subjects. In science classes, the comet served as a concrete example for teaching about orbital mechanics, spectroscopy, the scientific method, and the nature of comets. Students could learn how astronomers calculate orbits from observations, how chemical composition is determined from light, and how international collaboration advances scientific knowledge. Math classes could use the comet's velocity, distance, and orbital parameters as the basis for calculations involving unit conversions, scientific notation, and geometric concepts. Given the comet's speed of over 150,000 miles per hour, students could calculate how far it travels in a day, a week, or a year, connecting mathematical skills to real phenomena. Social studies classes could discuss the international nature of astronomical research and how scientists from different countries work together toward common goals. The fact that the Discovery Telescope was in Chile, follow-up observations came from observatories in Hawaii, Spain, and elsewhere, and that researchers from universities around the world collaborated on analyzing the data illustrated how science transcends national boundaries. Art classes could use images of the comet as inspiration for creative works, exploring how scientists create visual representations of phenomena and how false color images convey information. The stunning images from Hubble and other telescopes, with their dramatic tails and glowing comas, are both scientifically informative and aesthetically beautiful. Museums and planetariums created special programs about 3I/Atlas, using it as a focal point for teaching about interstellar space, the galaxy, and the place of our solar system within it. Interactive exhibits allowed visitors to explore the comet's trajectory, compare it to other interstellar objects, and learn about the techniques astronomers used to study such visitors. Online resources proliferated as well. Websites maintained by NASA and other space agencies provided updates on the comet's position, images, and scientific findings. Social media allowed astronomers to share their excitement and discoveries directly with the public, bypassing traditional media and creating a sense of connection between researchers and the people interested in their work. Amateur astronomers played a role in both the observation and the education efforts. Backyard telescope users captured their own images of 3I/Atlas and shared them online, demonstrating that meaningful contributions to astronomy are not limited to large professional observatories. These amateur contributions also inspired others to take up astronomy as a hobby and showed that the universe is accessible to anyone with curiosity and modest equipment. Chapter 25: Looking Toward the Future. As 3I/Atlas fades from view and continues its journey back into interstellar space, astronomers are already looking ahead to the next interstellar visitor and thinking about how to improve our ability to detect and study such objects. The lesson from the 3 confirmed interstellar objects so far is that they are likely more common than anyone imagined just a few years ago, and that better detection systems will find many more. The Vera C. Rubin Observatory, which photographed 3I/Atlas during test observations even before its official discovery, is poised to revolutionize the detection of transient and moving objects when it begins full operations. With its large telescope, wide field of view, and rapid surveying capability, Rubin will scan the entire visible sky every few nights, creating a continuously updated map that will reveal anything that moves or changes. Estimates suggest that Rubin might detect dozens or even hundreds of interstellar objects over its operational lifetime, transforming this field from the study of rare individual cases to a statistical population study. Other planned facilities and missions will also contribute. Space-based infrared telescopes that can observe comets even when they are far from the sun and only weakly active will extend the discovery space. Improvements in computing power will allow more sophisticated algorithms to sift through vast data sets in search of unusual objects. Machine learning techniques might identify interstellar candidates more quickly than traditional methods, reducing the time between detection and confirmation. When interstellar objects are detected in the future, the astronomical community will be better prepared to respond. Coordination networks are being established to ensure rapid follow-up observations, and proposals are being developed for dedicated observing programs on major telescopes that can be triggered when interesting targets appear. The goal is to maximize the scientific return from these brief opportunities. There is even discussion of potential future spacecraft missions to intercept and study an interstellar object up close. Such a mission would be challenging because of the high velocities involved, but it is not impossible. If an interstellar object could be detected far enough in advance, a spacecraft might be launched to rendezvous with it, either flying by at high speed to capture close-up images and measurements or possibly even matching its velocity for an extended study. The scientific value of such a mission would be enormous, providing data that cannot be obtained from Earth-based observations. A close-up mission could determine the exact size and shape of the nucleus, measure its mass and density, analyze the composition of surface materials directly, and perhaps even collect samples to return to Earth for detailed laboratory analysis. Such samples would be pristine material from another stellar system, offering insights into conditions and processes in regions of the galaxy we cannot otherwise access. While no such mission is currently funded or under active development, the concept is being studied by mission planners and aerospace engineers, and it remains a goal for future decades. Chapter 26: The Philosophical Perspective. Beyond its scientific importance, the story of 3I/Atlas touches on deeper philosophical questions about humanity's place in the universe and our relationship with the cosmos. The fact that an object formed billions of years ago in a region of the galaxy far from our sun could pass through our solar system and be detected and studied by intelligent beings is a remarkable convergence of circumstances. 3I/Atlas represents a tangible connection to the broader galaxy and to timescales far exceeding human history. This ancient comet existed long before Earth had oceans or continents, before life emerged, before the sun had ignited its nuclear fires. It drifted through space while stars were born and died, while galaxies collided and merged, while the universe expanded and evolved. The fact that we can observe and study such an object provides a humbling perspective on the scope of time and space. For most of human history, the sky was a mysterious realm, and comets were often seen as omens or supernatural phenomena. Only in recent centuries have we come to understand comets as natural objects, icy remnants from the formation of planetary systems. And only in the last few years have we confirmed that some comets come from beyond our solar system, linking us directly to the wider galaxy. This progression of understanding reflects humanity's growing knowledge and our developing ability to contextualize ourselves within the universe. The study of 3I/Atlas and other interstellar objects reminds us that the universe is interconnected. The atoms in our bodies were forged in stars that died before the sun was born. The water in Earth's oceans may have been delivered by comets during our planet's early history. The raw materials that made Earth and all life on it came from the interstellar medium, the gas and dust between the stars. In a sense, we are studying family members, distant cousins from other parts of the galaxy that share the same ultimate origin in the Big Bang. The realization that interstellar objects are relatively common raises interesting questions about panspermia, the idea that life or its building blocks might be transported between stellar systems by comets or asteroids. While there is no evidence that 3I/Atlas carries life or has ever been biologically contaminated, the existence of a regular exchange of material between stellar systems means that if life arose in one place, it could potentially spread to others. This remains speculative, but it is a concept worth considering as we learn more about the abundance and diversity of interstellar travelers. On a more immediate level, the story of 3I/Atlas highlights the value of curiosity-driven research. The discovery was made by a survey designed to protect Earth from asteroid impacts, but the scientific return extended far beyond planetary defense to fundamental questions about the galaxy and the diversity of small bodies within it. Supporting such research and maintaining the infrastructure of telescopes, computing systems, and trained scientists that make these discoveries possible is an investment in human knowledge and understanding. The conclusion: as this ancient wanderer slowly recedes into the darkness from which it came, growing fainter with each passing day until even the most powerful telescopes lose sight of it against the infinite blackness of space, humanity is left with a gift of knowledge and perspective that will endure long after the comet itself has vanished from view. 3I/Atlas arrived unannounced in the summer of 2025, a visitor from a part of the galaxy we may never visit ourselves, carrying with it the frozen chemistry of a time when our solar system did not yet exist. For a few brief months, this relic from billions of years ago passed through the sun's light and warmth, awakening from its frozen slumber just enough to reveal its secrets to the watching eyes of a curious species on a small blue planet. The story of 3I/Atlas is a story about discovery, and about the human drive to understand the universe beyond our immediate surroundings. It is a story about international collaboration, as astronomers from many nations work together to track and study the comet with every available tool. It is a story about the power of technology, from automated sky surveys that can detect faint moving points of light among billions of stars to space telescopes that can analyze the chemical composition of a cloud of gas surrounding a tiny nucleus millions of miles away. Most profoundly, it is a story about time and change on scales that dwarf human experience. 3I/Atlas has been traveling through space for longer than most stars in our night sky have existed, longer than Earth has been a solid world, longer than the complex molecules that would eventually give rise to life had formed. It witnessed the galaxy when it was younger and different, when the stars were arranged in different patterns, when perhaps other civilizations rose and fell on worlds we will never know. Now, having briefly passed through our corner of space and having allowed itself to be studied and cataloged, it returns to the silent void between the stars, where it will continue its journey for millions or billions more years until perhaps, by chance, it encounters another star, another planetary system, and maybe, if fortune favors it, another group of curious minds watching the sky. We will not see 3I/Atlas again. The comet is on a one-way trajectory out of our solar system, moving too fast for the sun's gravity to ever bring it back. But the data collected during its passage, the images captured, the spectra recorded, and the insights gained will remain with us, contributing to the slowly accumulating body of knowledge about the universe and our place within it. And when the next interstellar visitor arrives, as it surely will, astronomers will be ready, armed with the lessons learned from 3I/Atlas and eager to greet another ancient traveler from the spaces between the stars. The universe is vast beyond imagining, filled with wonders waiting to be discovered, and every now and then, one of those wonders comes to us, offering a glimpse of the infinite if only we have the wisdom to look and the patience to understand. This has been the entire story of 3I/Atlas, a frozen wanderer from the depths of time and space, and as it fades back into the eternal night from which it emerged, it leaves behind a legacy of discovery and a reminder that the cosmos is full of mysteries still waiting to be unraveled by those who dare to dream of the stars.